Okay, let's get started. A couple of brief reminders. Project 1 is due tomorrow, end of tomorrow. And one announcement, which is that homework 2, which was originally going to go out yesterday, is actually going out, was originally going to go out Tuesday, is now going out tonight. It may be posted already, but in any case, that's due Thursday of next week. So homework 2 got pushed back by 2 days. Okay, so I left this quiz on the slide here. Hopefully some of you had a chance to sort of think about this. Let's dive in and get back to alpha beta pruning. So at the end of last class, I sort of threw this slide up in front of you and said, this is what alpha beta pruning is. We don't have time to talk about it. So what is alpha beta pruning? This is this idea that like we want to be able to prune branches of this game tree as we're building it so that we don't have to do extra work. And how would that work for this tree? Right? So remember the blue nodes that point up, those are max nodes. The red nodes that point down, those are min nodes. And so if we're looking at this tree, we start by expanding along branch A. We get this min node. We start expanding its children. We look at branch B, and we see that there's this terminal node with a terminal utility attached to it. Our utility function tells us what the utility of this particular state is. It's 10, okay? And because this min node here is minimizing, we know that the value of this min node is less than or equal to 10. Before we even open up the other child, we know that the value is going to be at most 10 because we could always just take path B. If C is better, we might take path C. And in fact, if we open up C, which is what we do next, we see that there's an 8 there, so we can cross out this bound. We see that now we're less than or equal to 8. If there was another child here, we would keep going, but there's no other child, so then we can just say, all right, it's equal to 8. The value of this min state is equal to 8. And once we have that, we can go back up to this max node, and we can say, okay, well, the max node is going to do what it does. It maxes things. It has this path along branch A that gets 8 value. So the worst case possible value that this max node is going to get is 8. Right? So it's going to get at least 8, because it can always just choose to take A. We've solved the left side of the tree. We know that it has value 8. So worst case, the max node takes branch A every time, always gets value 8. Now we can open up the other side of this tree. We can look at branch D. We get another min node. The min node is going to be initialized so that it's minimizing, so it's going to be less than or equal to positive infinity. And then we see this 4 here, and we're like, okay, well, 4 is better than positive infinity, so now our bound is that it's less than or equal to 4, right? We cross out our old bound. And hopefully this is where you're seeing something interesting is popping out, right? So we know that the max can get value 8 by going along path A, right? So if it can get value 8 going path A, why would it ever open up D at this point? We know that the min node, it doesn't matter what's inside of F. F could be really big, it could be really small. We haven't opened up F yet. But the min node is going to take whatever's the smallest, and it's already found a 4. So at best, if you're the max node, the min node's only going to give you a 4. And that's not that exciting for you if you're the max node. So we go back up to this max node and we say, what was the max that you could do somewhere else? Oh, it's 8? Okay, then I don't have to keep expanding these nodes, right? At this point, I can prune branch F from the tree and we get some savings. Questions on this so far? Yeah?
Is there a way to reduce your initial bound from infinity to like some maximum that's smaller?
Well, let's think about that. So we want it to be the case that the max node picks the best option available to it, right? So if we were going to reduce our initial bound from infinity, I guess minus infinity for the max node or positive infinity for the min node, we would need some guarantee that we're not going to miss out on nodes that we would rather notice, right? So if we knew that the value of a state could only be plus or minus 1, then we could set the bound at 2, and then anything that we see, that would be totally fine. But it's also fine to just set it to be infinity, and then you kind of, the first time you see a node, it's going to be less than that. So yeah, good question. So you might be thinking like, okay, well, we only pruned one node. How useful is this? One node, that's not that much savings. Well, let's try and make the tree bigger, and we can see what happens, right? So here's another quiz. If you're following along on the recording, you can pause the recording now, and you folks in the room, you cannot pause the recording, unfortunately. Right, so let's try it here, right? So, okay, we have our max node at the top, we have 2 min nodes, and then we have another layer of max nodes. So this is different than before, where we only had one set of each. So first we're maxing, then we're minimizing, then we're maxing again, and then at the bottom we have our evaluation function, which is telling us 10, 6, etc. Okay, so we open the first child, we open its first child, we open its first child, we get a 10. So now this is a max node, so now we know that the value is greater than or equal to 10. We haven't opened up D yet, but we know that no matter what we see inside of D, this is going to be at least 10, right? This max node is going to take the best thing that it can find. We've seen a 10, so 10's a good lower bound. We could open up the successor here. That's a 6. It's not better than 10. So we actually know that it's equal to 10. We report that back to the min node. What does the min node say? Is this an upper or lower bound? The min node wants to minimize, so if it sees a 10, we know that the min node can get less than or equal to 10. Okay, cool. Can we prune anything yet? No. So we go down, we get into branch E, we get another max node. So the max node doesn't know anything yet, so it has to open up a successor. We see 100. 100, that's a lot of value. All right, that's nice. Good for the max node. The max node's like, all right, I can do at least 100. Nice, feeling good. What about G? Should we keep going? What does the mid node think about this 100? Does it look appealing to the mid node? Doesn't look so appealing to the min node. The min node's trying to minimize. So 100, that's not worth going down, so we don't have to keep expanding branches. We know that this is enough to guarantee that we always take B from the min node. Okay? So at this point, we know that we're always going to take B. This is no longer an upper bound. This is actually tight. So we have B is worth 10, and so the min node is worth 10. That's the value of the min node. And so now we've solved the left half of the tree. So now we go up to the max node, and we say, all right, well, the max node has option A. No matter what we do on branch H, it will always have option A, and option A is worth 10. So then the max node has value at least 10. Right? So then we go down H, we go down I, we go down J. J says 1. We're maxing. So what do we do at a max node? Max node says, well, 1 is better than nothing, so it's greater than or equal to 1. Then we look at do we look at its other child? Yeah, we do, because it could be anything, but all we have is a lower bound, and the max needs to know what else is in there. So, and why can't we stop early here? We can't stop early because if this is actually like something small, like it's actually going to be something small. If this is minus 1,000, like this max node could be what min picks, but up here, the max node is always going to choose the 10, no matter how bad this tree ends up being. So we have to look at this other 2. We end up seeing that the max node can do better than or equal to 2. Actually, can just do equal to 2 because there's no more children. Then we go up to here. We see the min node can say it's going to be less than or equal to that 2, right? Because the min node can always take I. No matter what L has, the min node can always take I. And now what? Should we consider opening up the other side of this min node? Can we look at L? Well, who would dictate whether we care about going down this branch? The max node at the top. And the max node says, if I go down A, I get at least 10. That's pretty good. If I go down H, best I can do is 2. So I don't care about this branch anymore. This is like so not interesting to me. H is so boring. Like all I have all I have in H is at best a 2, like I'm going to take the 10 every time. So I'll go down A, and I actually can prune this whole subtree. Pruning a whole subtree, that's a big deal. I mean, before we were just pruning a single node. Now we have a whole subtree. This could be an exponentially large subtree. It could be infinitely large. So now we can prune an exponentially large number of states from the tree. That's like a huge savings. Okay, so this is what it looks like when we have more than one layer. The more layers, the more you're going to potentially get to prune. Okay, questions on the 2-layer version or 3-layer version? This making sense? Nice. Yeah, on some level it's just mins and maxes, but it's important to remember what these numbers mean. All right, so here's the general version of it, right? Our tree could be arbitrarily large, and the way that we're going to do this is, where's my clicker thing? Right, so let's focus on the general case where we have a min node. We can deal with the max node in a second. It'll just be the reverse. So we have a min node. We're computing the min value at some node, n. N's down here. It's this last one in the tree. We're expanding n's children. Okay? We're looking at all of its children. We're estimating the minimum. The minimum could be potentially going down, potentially staying the same, depending on which children we're opening up. Okay? So we're looking at n's children. And we want to know, can we prune? Well, who cares about n's value? It's always the max node that cares about whether we're going down this path. So the max node is who's going to tell us whether we can stop expanding min children. What's the condition for that? Well, max has to have a better option somewhere, right? So this min node, n, has to be so bad that we would never expand the path down here. And for that to be the case, there needs to be some other node that's a descendant of a max node that's a better option, much more appealing than going to n. And so we're going to call that node alpha. We're going to say that if alpha is the best node that max can get to from any decision point of any max node along this path to get to n, then the max will always have a better option and we won't go down this path to get to n. So if n ever becomes worse than alpha, we can stop. Because it's already bad enough that it will never get picked. And then pruning the children of the max is symmetric. We're just going to use beta instead of alpha. So beta is going to be the best value that min can get along any branch. Alpha is the value that max can get along any branch, the best value. And these two things are totally symmetric, and we've already seen examples of how this works. How do we implement that? It's very much like minimax, right? We have this, well, the value function is the purple one. We got rid of that because we needed to say this part. But essentially, there's this value function. If it's a max node, it calls the max value. If it's a min node, it calls the min value. If it's a terminal state, then we call the utility function, right? And what we do is we just set the value to be equal to the max of that value and its successor. But we do this extra step now. We compare against our alpha and our beta. So we're keeping these bounds in our head. And we had to add Greek letters to make it confusing. You just compare against alpha. If it's, so on the min side, if it's less than alpha, stop looking, right? Just return the value. You're good to go. If it's greater than or equal, or if it's greater than alpha, you got to keep looking at children. Meanwhile, you're keeping track of that beta value so that if you ever come over here to the max, when you're checking against beta, you have an accurate beta. So each of these functions now takes in alpha and beta. And those values can change as you go down through the tree because it's always like the best value you've seen along a path that took you here. Okay, so the nice thing is that this pruning has no effect on the minimax value because we're only ever pruning stuff that we never care to go to, right? It's always so boring that we know we can prune it and it won't change anything. We would never even bother to pick that. However, the intermediate values, like these red values here, those could potentially be wrong. They could be potentially incorrect, right? So in this particular case, this one would be, let's see if I still have the pen on. Yeah, so this one would be 10. This one would be less than or equal to 10. And these are equal. So depending on how you do tie breaks, you might decide that this is like you could prune this. But the thing is, because those values are not, we haven't solved the right side of the tree, now the max node has a choice between a guaranteed 10 and a less than or equal to 10. And because we haven't looked at the full side of this tree, we have to be careful about how we resolve these ties at the max node and make sure that we go this way. So the naive version is going to potentially like choose between them arbitrarily, and that would be bad for the max node. So just keep that in mind. The values of these intermediate nodes might be wrong. So the way that you select when that's the case is important. But we also see that like the child ordering has an effect on when we can prune, right? If we see a good value first, like a good value for min, like if the 0 was first here, then we would know we would never go down this one. So then we could prune the 10 quicker. So maybe this is a bad example, but on this page, right, we knew that when we saw a good value for this min first, then we could prune this entire branch. And so that's nice. If we see them in the reverse order, it might be the case that we have to open up all the children before we can make that call. And if we had a perfect ordering, then this would actually decrease the number of levels in the tree by half on average. So we go from b to the m all the way down to b to the m over 2. And that's really great. It doubles the solvable depth. If you're looking in chess, you can think twice as far ahead. But you still can't enumerate the full game tree for chess. It's still kind of hopeless. So how can we handle search trees that get super, super large if we can still, even with all of the clever alpha beta pruning, if we still can't see all the way to the bottom of the tree, right? So we'll talk about that in a minute, but this is an example of thinking about thinking, computing about what to compute, meta reasoning. So this is a really key concept, and I'm imagining what the other player is going to be doing, they're imagining what I'm going to be doing, we're thinking about what is important to be thinking about. That's like a key concept in AI. That's going to keep coming back. Okay, so what if we can't see to the bottom of the tree, right? What if we're resource limited? We have a big tree like this. If we could get down to the bottom of the tree, we could potentially use our utility function to figure out what the value is, and then we can propagate that all the way back up the tree. But this could be exponentially large. It could be infinite. We might never get to the end of this game. So in realistic games, we just can't search to the leaves. We can't go all the way down the tree. So what do we do? Well, what if we didn't have to go all the way down to the bottom of the tree before we could tell how good the states were? What if we had some sort of estimate that could allow us to limit the depth that we need to search, so that if we just know how good those particular states are at the end of that depth limit, then we could solve the rest of the minimax tree above that, and then we'd be good to go, right? So imagine that somebody told us that the values of these states were -1, -2, 4, 9. If someone just told us that, then we could do the computations. It's just mins and maxes above that, right? So it's very easy if we just know these numbers. Obviously, we don't know those numbers, but we could potentially try to estimate these numbers, and then we wouldn't have to go down any further. If our estimate is good enough, then we don't have to go further down the tree. Right? So then we just, propagate these values back up to the top, and we're good to go. So if we have, let's sort of make these numbers concrete, right? If we have 100 seconds, and we can do 10,000 nodes per second, we can check 1,000,000 nodes per move. And so if we're playing chess, then alpha beta pruning allows us to reach a depth of about 8, which is, it's decent, but it's not great. I mean, if a person can think 8 moves ahead, that's actually kind of good, but those aren't always the most useful 8 moves, and so there's kind of a question of how can we improve this? Also, the guarantee, because we're estimating these purple numbers now, we're not going all the way down and solving the minimax tree. Because we're estimating those numbers, there's no guarantee that this is going to be optimal. We're just going to hope that it's good enough and we can make good decisions this way, okay? You can kind of think about this as like a heuristic almost, right? So in the classical search, right, we had this informed search heuristic that said, okay, it takes in a state, it outputs a real number. That tells me approximately how close to the goal I am. So you have to sort of squint to see how this is different from a heuristic. But here we're estimating the value of a state if I play optimally and my opponent plays optimally for the rest of the tree. So we're estimating the value of that state, which is sort of like about the future. And then in the planning case, in the sort of informed search case, the heuristic still takes in a state, it still outputs a number, but that number is what's the cost of getting to the goal from where I currently am, right? So it's slightly different context. Similar function though, okay? And we'll find that the more layers that we allow ourselves to search before we use this evaluation function, that really helps us, that the evaluation function doesn't have to even be that good. As long as we have a sort of a deep search before it, we'll be okay. And we can also use, so back in the first search lecture, we talked about iterative deepening depth first search, right? So you can use the same concept here. We talked about iterative deepening A star in the A star lecture. You can use the same idea and you can increase the depth over time. So first, maybe you start out with a depth 1 search. You have your evaluation function. It looks at the states, it inspects them, and it says, okay, well, here's the value of that depth 1 search. If you still have time, you know, we have 100 seconds for this particular example, like you can keep going. You say, all right, well, I'm going to run a depth 2 search. If I finish in time, I'll have a better action selection, right? And if I still have time after the depth 2 search, I'll run it again, right? I'll just run it with depth 3. As long as I still have seconds, I can still compute, and maybe I'll get a better and better answer as I go. So that's how we can kind of handle resource limits. It's basically this guy checking how good a state is, and we're going to use that to help us prune or stop our search early, right? So our search tree might look like this, and each of these nodes, these states, they're not the end of the chess game, right? These aren't the ends of the chess game. There's no checkmate yet. These will have long, potentially exponentially large search trees below them, big game trees underneath. And what we're doing is we're saying, you know, I'm just going to stop the search here. This is all the time I have. Let's see how good those 3 states are. And so you look at this state and you say, okay, well, it's black's turn. Maybe white has, you know, the same number of pieces, but white has more control of the center. White might be doing slightly better. Over here, black has captured a lot more of white's pieces. It's white's turn. Maybe black is winning this game at this point, right? Up by 3 pieces. So some sort of evaluation function takes in these states and tells us how good is this for each player. How good is this for the starting player? So ideally, we want this evaluation function to be the minimax solution, right? It would be super, super nice if this just told us the value of those states. Then we wouldn't have to look at the states. We could trust it completely. We'd be good to go. This is going to have the same problem as using like an exact heuristic. So we can't use the optimal minimax value because if we could, we wouldn't have to evaluate it, right? The only way to get that value is by running the whole minimax search, and we can't do that. That's why we need the evaluation function in the first place. So we can't use the ideal function, but we can hopefully use something that's pretty good. So we're going to look at the features of this particular state. We're going to look at the features of that particular state, and then we're going to just make up an estimate of how good we think the state is. Usually that's going to be a weighted sum of features. So we're going to have a feature for calculating maybe the sum of the number of white queens minus the number of black queens. Queens are like really important pieces in chess. They can attack a lot of squares. They're very powerful. If you lose your queen, it's not a good thing, generally. So this is one feature. Sometimes there's like queen sacrifices, and getting rid of your queen is okay because it sets you up to do something else. So it's not the only feature that's important. It might also be important like whose king is under attack. It might also be important who controls the center. How many squares can your bishop see? Like all of these things might be features of the state, and we can see what those features look like. Each one of those is going to give us a number, and then we're just going to combine those with a weighted sum. So we're going to add them up, weight them appropriately. More important features will get bigger weights. Features that help player 1 will get positive weights. Features that help player 2 will get negative weights because they hurt player 1. And so with these weights, we can essentially sort of combine these different features flexibly and hopefully come up with a function that's good enough for estimating the minimax value for the rest of the tree. Yes, question? Yeah, evaluation functions are like heuristics because they take in a state and they output a number. A heuristic is really focused on how many steps am I away from the goal, right? How much is it going to cost me to get to the goal from where I am? And here we're not looking at costs. What we're looking at is what's the value of finishing the minimax tree from this particular state. So just the point of using the function is slightly different. We're using it here to estimate the minimax solution, and in a heuristic, we're looking at how much does it cost me to get to the goal. But yeah, they otherwise are quite similar.
Why does the example function choose the number of queens on white minus the number of queens on black? Isn't it just 1 and 1?
In this case, it's 1 and 1, yeah, but it's possible if you move your pawn to the back rank, you can get 2 queens. It's possible that if you take the opponent's queen, they could have 0 queens. If you have a lot of queens, that's going to be good for you. So yeah, I mean, where do these features come from? We make them up. We think, this might be helpful for estimating the minimax value. So we put it in there. And then how do we learn the weights? That's going to be later in the course when we do machine learning. But this concept will keep coming up. It's like, we can even use like complex neural networks to build these functions. But like, it's a core machine learning concept to take features about a problem, take features about a state, and then flexibly combine them either in a linear way or a nonlinear way, and then come up with some function. Okay, so back to our favorite game. How would we design an evaluation function for Pac-Man? What's the value of this state? I don't know. How would you even start? Well, maybe it's easier to compare this state to another state, right? We can decide which one we like better. Do we like this state better, or do we like this state better? First one, because it's, I guess, safer, right? Okay, so if this state is better than this state, what about this state? Between these two states, do we have a preference? Well, one, we've eaten more dots, but otherwise it's kind of the same. I don't know, maybe one's better than the other. We could sort of decide with some, we could make an argument for one way or another. Probably we like those states better than this state though, right? Not the best for Pac-Man. This one's even more dire, right? That's actually so depressing. Let's go back to this one. We could imagine like comparing these things, right? And so if we see this state and we see this state, we might not know what the value of either of those states is, but this will give us an idea of what features are important for deciding between these two states, which do I like better. Like maybe something to do with the distance to the ghosts, maybe something to do with how many dots we've eaten already. If I'm surrounded, that might be an important feature. There's lots of things that we could consider here, but by comparing these states, that might be helpful for designing these kind of evaluation functions. Okay, what can go wrong when your evaluation function is not great? So let's try this video, see if it plays. Okay, so Pac-Man's going to think for a while. We'll just jump ahead. So Pac-Man's using an evaluation function here. Takes a first move, takes a second move, goes back to this state, goes back to, uh-oh, hold on. What's going on here? Why is this happening? What did we do? Okay, so this is kind of a busy slide. Let's start with the left tree. Okay, this is time 0. We're doing our planning. Let's say we've just simplified the problem so it's one-dimensional, right? So there's 2 dots to eat. Pac-Man's in between them. Pac-Man's on the left side. There's 2 actions Pac-Man can take. Can go left, eat the dot, or right, not eat the dot, right? Let's suppose we're going to do a depth 2 search, and then our evaluation function, someone told us that our evaluation function is just the score that we generate, right? So if you remember the rules of Pac-Man, you get -1 for every step you take, and you get 10 for eating a dot. So you're going to eat a dot in this route, so you get 8 minus the 2 to take you there. You eat a dot over here, that's 8, and then here it's -2, because you didn't need a dot, but you took 2 steps, okay? So we can do the whole mini-max thing. Actually, it's just max, because there's no adversary here, so we take this 8 up to here, we take this 8 up to here, we take these 8s, sort of, doesn't matter whether we go left or if we go right, because after 2 moves, we're going to get the 8, right? So we don't have any preference between going left or going right. We break ties. Let's say that arbitrarily we break ties like this, right? We go to the right. Now, in Pac-Man, we will have adversaries, and the adversaries may not always do what we expect. So sometimes it's going to be useful to replan. Essentially, like, if the adversary takes an action that we weren't expecting, we may have pruned an entire section of the tree that would be useful for choosing actions if only we had known that the adversary was going to do that, right? So now they're taking actions, they're surprising us, right? We haven't really planned for this. We didn't think about that section of the tree. So we might need to replan. And in this case, we're just replanning every step just in case. So this state essentially goes over to here, and we decide we're going to replan from here. Okay? So now we're on this side. Time step equals 1. Again, we're going to use our evaluation function. The lords of Pac-Man have decided this is worth 8. That's 8. This is -2. Same as before, but sort of flipped. We can do our mini-max thing, or our max-max thing. We get 8s here. We have no preference. The starting state is worth the same thing, right? So we break ties arbitrarily, and just to make things fun, we'll just say we break the ties this way, right? And so what are we going to do? This state, if we replan, takes us right back here. So because we don't have a preference, because we're breaking ties arbitrarily, we're stuck in this loop where we don't care whether we go left or right. We might as well go right. We'll replan when we get there. We don't care if we go left or right. We might as well go left. And so Pac-Man starves because all of these things look good from a depth of 2 search with this particular evaluation function. So what's going wrong here? Oh, it's just not that good of an evaluation function. Like, what is it saying is the value of some of these states? Like, it's saying, first of all, this state and this state have the same value. Does that feel right? One of them were closer to a dot than the other. Or to put it even more succinctly, like this state where we've eaten a dot and this state where we haven't eaten a dot, those both get the same evaluation too. So how good is this evaluation function? It's not really helping us to figure out the minimax value. Partly because this evaluation function isn't like distinguishing between these kinds of states. So if you have a bad evaluation function and you have a short depth, then you're not going to necessarily be able to make good decisions. And that's what leads to this thrashing thing. If we added something like, how many dots have we eaten, or what's the distance to the closest dot, we could get into a situation where we actually fix the problem. Right? So if we add a better a better evaluation function, Pac-Man just eats the dot, goes about his business, eats the other dot, and we're good to go. Nice. So yeah, the depth of this search matters. The quality of the evaluation function matters. Evaluation functions are always going to be imperfect, right? Because we can't afford to solve the whole minimax tree. But the deeper in the tree that evaluation function is buried, the less it matters if it's like super, super accurate. As long as it's like loosely accurate, kind of gets it right most of the time, like it's okay, as long as we've taken a while, like a lot of steps to get there. So there's this same trade-off that we saw before. Like we could have a really accurate evaluation function, just like we could have a really accurate heuristic. It might take a long time to compute this evaluation function, but maybe we feel like that's an acceptable trade-off because it means that we don't have to do as deep of a search. Or we might want a really cheap evaluation function because we can compute, maybe the branching factor is not that big, we can compute pretty deep, and we just want to be able to evaluate the evaluation function on lots of nodes. So now there's this trade-off again. Okay, let's see if we can see why depth matters.
So here's a configure be closer or
sort
farther
of
from the dot.
A contrived example. I'll pause it for a second. So Pac-Man has to decide how to act in this game where now there's 2 ghosts. There's 2 ways to get to the dot, and we don't know necessarily what the ghosts are going to do. So Pac-Man is planning ahead, building out this game tree, mini-maxing, potentially for some depth. In this case, the depth is going to be 2. Depth 2 is not going to be enough. Essentially what's going to happen is, at some point, Pac-Man's going to decide to move.
2 ahead. We're going to move
down
towards the dot, unsurprisingly. Except
takes
now
a
what
while
happens?
because the ghosts have to sort of compute what they're going to do too, and then Pac-Man recomputes.
We get pinned.
Pac-Man gets trapped. Pac-Man essentially couldn't look far enough ahead to figure out how to avoid this particular scenario. But if you look deeper, this is kind of a really interesting example, because if you look deeper, Pac-Man takes a really weird, unusual, kind of counterintuitive first move. Right? So Pac-Man actually goes up first. And you might think, like, well, why would Pac-Man go up? That's like towards the ghost. But the depth 10 search that we're running here has like a mastermind plan. It's thinking like, well, if I go up for 1 step, it's going to buy me some time so that I can see where the blue ghost is going. And because Pac-Man moves just before the ghost moves, Pac-Man will still be able to get away. So what does buying that time afford us? Well, once we buy that time, and these ghosts and Pac-Man sort of do a bit more computing, Pac-Man goes down, evades the orange ghost, and now the blue ghost is going to the right. Pac-Man can go to the left, and the blue ghost is committed at this point, so Pac-Man can actually go around and win, right? So the deeper search allows us to find that solution. So this should show like kind of how the depth can be useful. With a depth 2 search, you can't find that solution. Okay, so I'll just throw this slide up for a second. There are some synergies between the evaluation function and alpha beta pruning. If your evaluation function is useful, it can actually give you guidance about which nodes to expand first. And that can be helpful because if you expand the good ones first, then you can prune a bunch more. So I'll just say that. There was a question in the back. What was the question?
My question was mostly going back to the source of flashing. Was the issue with the source of flashing related to the depth or the values that were coming?
You're talking about why does Pac-Man stop eating the dots?
Yeah.
So can you say the question again?
Yeah, like when you were explaining flashing earlier,
Yeah.
does that have to do with how deep the tree goes or the values assigned?
Okay, great. Yeah, great question. So the question is, when Pac-Man starves, does this thrashing behavior have to do with the quality of the evaluation function, or does it have to do with the depth of the search tree? I think the answer is that it's a bit of both. Okay, on the one hand, we're getting a bunch of 8s evaluating all of these nodes, and some of them feel like they shouldn't be getting the same value as each other, so our evaluation function is bad. Some of it is also like how we're breaking ties. So like sort of breaking them arbitrarily, and it's a little bit cooked up so that this interesting thing happens. If we broke ties in a bit saner of a way, maybe we would avoid this, but it's hard to come up with a tie-breaking strategy that avoids this every time. And then as for the depth, yeah, if you had a deeper search, eventually you would see that like in some of these cases you're actually eating 2 dots, and those would be preferable outcomes to the ones where you're eating 1. But the evaluation function is definitely playing a role here as well. So part of it is, I think, depth, and part of it is the evaluation function. Thanks for the question. Are there more questions? Yes? Yeah. Let's see. Here's a slide where that's the case. Right. Right, okay, that's a nice point. Yeah, so the point is that if this was happening, but we were over here, and Pac-Man was about to eat the power dot. I see. So if this were a power dot, then now we could eat these ghosts, and that would be super good. Yep, you could lead the ghosts up here, you could eat this one. Yeah, so I agree. Taking these power dots into account is definitely a feature that we would want to add to our, our weighted evaluation function for sure. Yeah, good point. Other questions before we move on? Yeah. Uh-huh, that's exactly it. Yeah, the depth is how many steps ahead we're looking. Okay, let's move on. Let's talk about uncertainty. So there's other games, right? There's games with dice. There's games like real life, where random stuff seems to happen all the time. How are we going to handle this? Today's code is roulette because they're spinning a wheel. Yeah, gambling. It's not good. All right, so folks got the code? Ready to go? Nice. All right, so yeah, uncertain outcomes, right? Like what happens if one of these agents is rolling dice? What happens if the world is rolling dice on us? How are we going to handle these cases? Before we had this minimax tree, we could compute the value, right? We got 10 on one side, we got 9 on the other, and that's like pretty easy. We all know how to do mins and maxes by this point, hopefully, right? So the max is going to take the 10, we're going to go this way, and then we're good to go. Remember, we said that this is optimal if we assume that we are making optimal decisions and the opponent is making optimal decisions. We're maxing, they're minimizing. It's like this, right? We're playing tic-tac-toe against this supercomputer. But what if we're playing against this guy? I showed this slide last time. If this guy is making mistakes, then it might be the case that they're leaving us this 100 some fraction of the time, right? Could be all the time, could be some of the time, but if they're sometimes giving us this 100, then maybe we want to make a different decision at our max node, right? We might want to exploit the fact that they're giving us more value for free. Yes? Does pruning eliminate uncertain outcomes? Well, so pruning and uncertainty kind of don't play that nice with each other. Pruning is more about, yeah, I guess in some sense you haven't expanded that side of the tree, so you're not sure. It's a bit of uncertainty about what that side of the tree contains. Yeah, so in that sense, yeah, it does eliminate certain outcomes, but these are outcomes that would never occur because in the minimax search, if you're pruning like this one, because the min sees the 9, right, you can actually prune this node because 9 is worse than 10, and so we'd never even see that side. We would never see that side assuming optimal play for both players. But the minute that this guy is making moves, we might actually see that, right? Because he might not be doing the minimize operation. He might be doing something else. He might just be doing this, right? So, yeah, so we can prune when we know who's making which moves and that everyone's doing the minimax thing. But it's going to be tricky to do that when there's probabilities involved. And we can treat this guy as just rolling dice because we don't know what he's going to do. Or it could be the case that we're playing a game like backgammon where you actually just have to roll dice before you move. And so this idea of moves being controlled by chance and not by the adversary means that we can't always use min nodes for this. We sometimes are going to have to use chance nodes. So this is going to capture the idea that randomness is just affecting the outcome, and it's not guaranteed that it's going to be the minimum or the maximum anymore. So these are chance nodes. This leads to what's called Expectimax search. So instead of minimax search, we're going to have an expectation in place of the minimum, and this is going to be Expectimax search. Yeah, was there a question? Yeah, so in chess, yeah, it's not solved yet. In checkers, it's solved. In tic-tac-toe, it's solved, definitely. But yeah, as you said, we're above expert level with chess, but we haven't solved the game. So the question is, does that mean there's probabilities involved? We don't know what move we're going to take. It depends on the chess engine. But yeah, because we haven't solved it, you could treat the uncertainty about what your opponent's going to play as essentially a chance node if you wanted to, yeah. So this doesn't have to be the opponent is just actually rolling dice. This doesn't have to be you're playing backgammon and there's dice that you have to roll or you're playing Settlers of Catan, right? There might not be any dice in the game, but you can still model your opponent as making a probabilistic decision And then you can still throw a chance node in there to help you capture that. Okay, so the values now aren't going to be minimum values. They're going to be average case values. We're going to find the expectation of these chance nodes and figure out how much value on average does this particular node get to. So if I go to the left with some probability, let's say 0.5, and I go to the right with probability 0.5, then the value of this node is the weighted combination of these two things. It's the average of 9 and 100, which is, well, it's 109 over 2, right? So that would be the value if we propagate it back up through the chance node. Each chance node is going to come with probabilities associated with it, right? So it's going to have certain outcomes. Those outcomes are going to have certain probabilities. We'll get to sort of a quick review of probabilities in a second. But the chance node, someone is going to provide us with a chance node, and then they're going to provide us with the associated probabilities. We'll worry about sort of where those come from later. Okay, so it's not the worst case outcome, because it's not minimizing. It's the average case outcome. So this leads to Expectimax search, right? So max nodes are the same as before. Everything is the same as in Minimax for max nodes. We're trying to get as much value as possible, but our environment or our adversary is making decisions randomly, and so the next state will be governed by these chance nodes. We're just going to compute them. They're like min nodes, but now the outcome is uncertain, and so we're going to calculate expected utilities. So eventually we'll get to MDPs. I'm not going to make that connection now. All right, so here's the pseudocode. This should look very familiar. These are all kind of the same. Right, we have some dispatcher. It says if it's a terminal state, just return its value. If it's a max node, do the max thing. That looks like this. And then if it's a min node, now we're going to, or sorry, if it's an expectation node, if it's a chance node, we're going to do this expectation value thing. Right, so for each successor, it's going to have a probability associated with it. We'll capture that. And then it's going to have a value associated with it. We'll capture that. We'll multiply those two things together, add them all up, and that's how we compute the expectation, just an average. It's a probability-weighted average of the outcomes. So what does that look like for an example? Well, we're going to look at each successor in sequence. So we look at the 8 first. It has a half probability, so that comes to 4. We have a 24. That has a third probability. That comes to 8. And we have a 6th probability of the minus 12. We can add these things together, weight by the probabilities, and the outcome is that the expectation value of this chance node is 10. Otherwise, these trees look exactly the same as before. So now we're just going to handle the green nodes differently, right? So we have 3, 12, and 9. Let's say that they're, for the sake of argument, that they're equal probabilities. That's going to give us an 8. This one's going to give us 4. This one's going to give us 7. Hopefully I did that right. Okay, 8, 4, 7. So then the max node does what a max node always does. It chooses the best one. So it's going to choose this one. It's going to say, I don't know which outcome I'm going to get, but it's probably going to give me value 8 on average. It's not going to give me value 8 ever. It's going to give me value 3 or 12 or 9. But on average, it'll give me value 8. And that's better than getting 4 or getting 7. Okay? So someone asked, what about pruning? What about chance nodes and pruning? Can we do this? Well, it gets really complicated. Essentially, what we were doing before, why we were able to do pruning, was we were imagining what it would be like to open up these nodes, right? So we looked in there and we kind of hypothesized, right? It could be 1,000. Could be a minus 1,000. And we said, all right, well, if this node was a minimum node, then it would just be less than or equal to 2. And then, we could prune if we already had a better option than 2. But when it's a chance node and we're taking the expectation value, we're going to be averaging all these things together. If this is 1,000,000, and this is, doesn't even matter. Like, the 1,000,000 is going to affect the average, right? So now I care whether this next one is minus 1,000,000 or it's plus 1,000,000, right? Because the average is going to be plus 1,000,000-ish, or it's going to be about 0. So now these values are important. We can't just ignore them. No matter what we saw already, no matter what other options we had in the tree, Like, we have to open up all of the successors. Otherwise, we're not going to know what the expectations are. So we'll get into ways that we can still get some sort of resource savings in a bit. But pruning is not going to work for us anymore. But it does work to limit the search depth, right? So the same as before, if we have a decent evaluation function and it's too expensive to expand this whole tree, we can add our evaluation function in here. We don't have to compute the terminal utilities. We can just compute the evaluation function values for this particular state. And then we can propagate those backwards up the tree according to the chance nodes, and then we take the max. So this will be our estimate of the true value of doing the whole Expectimax search all the way to the bottom of the tree. Just as before, it was an estimate of the minimax value of running the minimax search all the way to the bottom of the tree. Okay? Yes?
Would we have to change our evaluation function, or can we just keep it the same like for minimax?
Yeah. Would we have to change our evaluation function, or could we just use the minimax evaluation function? What do people think? Well, if we have an estimate and it's 300, what does that mean? It means if I run, let's say we start with minimax, right? This is our minimax evaluation function. It says if I run minimax to completion, I'm going to expect, on average, that I get 300. Let's go back to, I think a better slide to illustrate this would be maybe this one, right? So let's say we have some evaluation function, and it's telling us that this node is a 9, right? So if our adversary is this guy, totally accurate, that's going to give us the right evaluation. We know that this node's value is totally 9 when it's this guy. But if it's this guy, it might not be 9, right? So our evaluation function kind of needs to depend on what algorithm we expect the other guy to be running, right? So if our adversary is running minimax, then we can totally afford to be pessimistic and use minimax. If our adversary is doing we don't even know what, then like we kind of can't afford that because it won't be optimal anymore. So we might need a different evaluation function in that case. Thanks for that question. Okay, let's talk about probabilities real quick. Hopefully this will mostly be review. Yeah, question. Sure. Okay, sorry, yeah, I went a little quick here. So this is saying like if there's a 1/3 on each of these outcomes, then this one gets a 1, this one gets a 4, this one gets a 3, and then I just add these together and we get to 8. So we're just taking the average. But yeah, where did those probabilities come from? I just made them up. So normally our chance node would say that these have to be a 1/3, or it would say that they have to be something else. I just made up that they were a 1/3 to make the math go easy. Yeah, exactly. Yeah, so we'll do a bit of review on probabilities right now, and that'll explain where these expectations come from. Yeah, so remember that in probabilities, we have these random variables. They can be anything. Well, actually, they can't be anything. They have certain events, these are certain outcomes, and they all have sort of probabilities attached to them, right? The probabilities have to be non-negative. They have to sum to 1. It means something has to happen. And so we could have certain events, like maybe we're thinking about traffic, right? We're thinking about driving to the airport. The road might have no traffic with probability 0.25. It might have some traffic, probability 0.5, or it could have a lot of traffic. I mean, this might not be the Bay Bridge because this one would have a lot more probability. But okay, so we can assign outcomes, we can assign probabilities to those outcomes, and there's different laws of probability that we have to follow. Hopefully most of this is review. If we see that if we have some extra information, like we know that it's early in the morning, it's like rush hour, we might know that there's gonna be more traffic than if it's not rush hour. We'll get to sort of updating our probabilities based on events. That stuff comes later. But with expectations, all we have to do is we say that the expected value of a function of a random variable is the average of that function weighted by the probabilities for that random variable. So how long does it take to get to the airport? Well, let's think about all the possibilities, right? There could be no traffic, there could be some traffic, there could be tons of traffic. Each one of those has a probability associated with it. And the time it takes to get to the airport might be one of these three numbers, right? 20 minutes, 30 minutes, 60 minutes. To get the expected wait to get to the airport, the expected travel time, we have to multiply the probability of each outcome by the time for that outcome, and then we add these times together. So this gives us a weighted average of 35 minutes. It's not going to actually take us 35 minutes. It could be more, could be less. It's going to be one of these three outcomes for this particular random variable. But on average, if we add up lots and lots of different trials, it's going to be about 35 minutes on average. So that's how we compute these expectations. And that's what's going on inside of the chance nodes. We're just computing this expectation. Right? And so we talked about sort of where do these probabilities come from. I haven't told you where they come from. I said, we either make them up, which is what I did, or maybe the probability fairy comes and gives them to us, right? But somehow these chance nodes get imbued with these probabilities. Later in the course, we'll figure out where those probabilities come from. But these probabilities can be used to model anything from like actual randomness in the world, like random dice, or it could be that we just don't know things about our adversary. We don't know like how they're going to behave. And it can get quite complicated. Like the model might say that the adversary is likely to make a minimax calculation, but it might not, right? Like we can kind of combine these ideas together. Okay, so for now we're just going to assume that someone tells us the chance node probabilities. And this is important for Pac-Man because in Pac-Man we have, Pac-Man takes a max turn, then the ghost moves randomly, and then the next ghost moves randomly, and then maybe the next ghost, and then Pac-Man gets to move again. And so it's a max followed by a bunch of chance nodes. So this will be an Expectimax search. Okay, so let's think about this. Imagine that you know your adversary is going to run a depth 2 minimax search. Use the results of that minimax search 80% of the time, and then the remaining 20% of the time they're going to move randomly. Okay, so think about this. What would you want to use for your search tree if that was how your adversary was playing? So 80% of the time they're running minimax, and then the rest of the time they're just picking randomly. Yeah? We could use minimax just to be safe. Now, what if the remaining 20% of the time they're picking actions that are really bad for them, really great for us? So if we use minimax, there's some amount of value that we're leaving on the table that we could be getting. If we chose to use chance nodes, then we might be able to recover some of that value. So I agree with you. It is safer to use minimax. It's sort of pessimistic, but there's always this question of like, could we be getting more value out of it? Yeah. So one answer is you could use Expectimax. You could build your tree like this. And to figure out each node's chance probabilities, you could actually run a simulation of doing minimax inside of that node, right? So you imagine, ooh, if I get to this chance node, really I have to do a depth 2 minimax search. And then once you run this, maybe it says always go to the right, okay? Always go to the right times 0.8 for 80%, and then times, uniform for the remaining probabilities. So we could get, 0.8 goes here, and then we split the remaining 20% between the two outcomes. So you can compute these chance node probabilities by running a minimax search inside your head. You're really thinking hard about what the opponent's going to be doing. And that winds up calculating for you what these chance node probabilities have to be. So if you really want to think about what the other agent is going to do, that can help you to calculate what these chance node probabilities will do. And then you will make the right decision sort of on average. It won't necessarily be the safest decision, though. So if you need the safest decision, you want to make sure that you can't be exploited. Maybe the minimax solution could be better there. But doing this whole computation gets slow, right? You could probably imagine that this would get slow. Because every time we get to a node, we have to then build a search tree, run minimax, and figure out what the answer is, just to compute the chance node probabilities to keep running our original search. That's a lot. That's like probably going to be pretty tough to keep up. One nice thing about minimax is that you don't have to do any of this stuff because it just collapses into a single tree. So when you are doing minimax, you get some savings. And that's partly why you can do the alpha beta pruning. Okay. So yeah, we sort of alluded to this already, but our modeling assumptions are pretty key here. We're building this model of another agent. We're building a model of the world, a model of how backgammon works or how chess works. And the more accurate this model is, the more useful it will be to us. But if it's too expensive to compute with, it might not be that useful because now it's expensive to run it. So if you have a really high fidelity model, it might be too expensive to run. If you have a really low fidelity model, it might be useless to actually use it. So yeah, we talked about, you could use minimax and you could then avoid the problem of, at least you would be safe, right? So if you're too optimistic, you might think that these are chance nodes when really they're adversarial. And you're sort of like this robot, right? You got your rose-colored glasses, you're walking around thinking everything's fine. You come across this cave, your rose-colored glasses means that you can't see those sort of red faces in there, and then you might just walk inside and see what happens. This is not great. We would like to maybe avoid that. This is potentially the danger of optimism. On the other hand, there's dangerous pessimism, where we think, okay, I'm going to just assume the worst case no matter what, even when it's not that likely. And so you might be freaked out by this little bunny because you think something bad's going to happen. But nothing's bad's going to happen. Like, it would have to be like a really unlikely bunny for that to be a problem. Okay, so here's a demo of getting these things wrong. Hopefully these, yeah, I'm going to skip this one actually. Let's do this one. No, we'll actually do this one. Okay, yeah, so Pac-Man's trapped between these two ghosts. What's he going to do? Well, if he's pessimistic, there's no real point in sort of going for the dots. We don't know where the blue ghost is going to go. He could move towards Pac-Man. He could move away. Pac-Man just sort of crashes right into the orange ghost because there's no hope, right? Too pessimistic. And where did we see that the blue ghost went? Blue ghost actually went down, right? So there might have been hope for Pac-Man in this scenario. Okay, so what if Pac-Man decides, I'm just going to be a little bit more optimistic. Maybe I'll move to the left. We don't know where the blue ghost is going to go, right? Like, the blue ghost could be acting randomly. It might still go up, in which case we're still screwed. But there's the possibility, I think it's later in this video. Yeah, there's a possibility that the blue ghost won't go up, right? The blue ghost could still go down some of the time, and if it's acting randomly, maybe we'll get lucky. If we go over there, we might get the dots. So where your expectations are and what reality is, there's sort of this expectations versus reality, how they line up. And in each of these cases, Pac-Man does better or does worse. Like, when you have an adversarial ghost, you tend to do worse, no matter what your assumptions are, because that's just a harder adversary. When you have a random ghost, you can do better if you assume they're acting randomly than if you are too pessimistic, right? You can actually extract extra value because you're not being so pessimistic. So what does that look like?
Well, what's going to happen? What's going to happen is you basically go straight for the dot.
Imagine you're in this situation,
what's
right? And you assume, okay, random ghost, Expectimax Pac-Man. That means that your assumptions match reality.
What's going to happen is you basically go straight for the dot.
We just go for the dot because it's pretty unlikely that they'll come for us. Versus now we have an adversarial ghost and a minimax Pac-Man, so that our assumptions kind of match up again.
So because it's going to get on top of you and you're going to die.
Lead them around
so you
the
kind of
corner
lead it on a
and
chase,
then safely get the dot
and you do
once
the
they're
safe
sort of
thing.
out of the way. But if our assumptions are mismatched, we'll be in sort of
ghost
these
is coming right at you, but you
where,
take a risk. You don't know that. Well, you're going to take it right for you, but you don't know that. Well, you're going to take a risk.
for it, and then the ghost is
and the ghost is coming right at you, but you just can't imagine it's true. And you keep taking these risks.
And so it's
maybe
like
it works out, or maybe it.
We won't actually even eat the dot. Sometimes the ghost will eat us. And in this case, it's like we assume,
actually not particularly
even though there's a random ghost, we assume that it's adversarial. We assume it's doing minimax. And so what's going to happen is Pac-Man is going to go and like hide because it's too scary to go close to the ghost. The ghost isn't even like doing anything. It's just like randomly running around. And Pac-Man's like, I can't even. It's too much. So eventually the ghost, eventually will get out of that zone just randomly because this happens eventually.
No.
And once it's finally out of the way, Pac-Man can go and grab the dot. But this is where like our pessimism about the world is actually screwing us over because like if we were a little bit less pessimistic, we could like just go and eat the dot and not worry about it. Okay. So we talked a little bit about other game types last time. We can add even more other game types to the list, right? Now we have these chance nodes. We can think about games like backgammon. We can think about Expectimax. But we can also think about Expectiminimax, right? In backgammon, I take a turn, then you roll the dice, then you take a turn, then I roll the dice, then I take a turn. And so we can actually stack these, and everything works exactly how you would expect. If you want to compute the value of this max node, first compute the chance nodes. And before you compute each chance node, first compute the min nodes. So this works exactly how you'd expect. And this allows you to do things like backgammon. So backgammon was actually solved in like the early 90s by this program TD Gammon that used depth 2 search, but it was Expectimax search, and then it just used a very good evaluation function, and they got to like world champion level play. It was like one of the first games to do that. We talked about this last time, so I won't dwell on this, but you can have multi-agent utilities, and so you could have like, you know, a max, 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 but now they're maxing over different things, right? You have these different utilities. Notice how like if red goes to the left, now we have the green and the blue utilities are like either 6, or they're both like 1 and 2, or 1 and 2, or 2 and 1. Like it's either good for blue and green, or it's kind of bad for blue and green. So red, if red chooses left, it's like blue and green's utilities are now correlated along this left side of the tree. Whereas if red chooses right, blue and green's utilities are sort of like anti-correlated. What's good for green is bad for blue and vice versa. So what happens is, like we talked about this last time, like green and blue could emerge some sort of cooperation if red chooses left, or they could emerge competition just based on these utility values and how they kind of stack up. So it could be like this, where green is helping blue, or it could be that like blue is playing against green. All right. So we talked about Expectimax, and we said, you know, it's tough to do this sort of alpha beta pruning stuff because, you know, all these different chance nodes outcomes makes it difficult. Is there another way that we could tame the scope of this ridiculously large search tree? And the way that we're going to do that is called Monte Carlo tree search. This is a picture of Monte Carlo. It's a place in Monaco where they have casinos. This is why there was that roulette wheel earlier. Yeah, lots of gambling, lots of probabilities. Monte Carlo tree search. Essentially, there's 2 simple ideas inside of Monte Carlo tree search. And what it's doing is it's trying to fix this problem where methods based on alpha-beta search, they assume a fixed horizon. And that's going to be pretty hopeless for Go, which has a branching factor of like 300. So in the first level of the tree, you have to compute 300 successors and evaluate them. If your evaluation function is more than like just a tiny little evaluation function, that's going to be very expensive. But the next level of the tree is going to be even worse. Now you have 9,000 nodes. Okay? So this gets really expensive fast, or is it 90,000? So it gets super expensive really quickly. Monte Carlo tree search is going to try and tame that complexity, and it's going to do it with 2 different ideas. One of them makes total sense. The other one is kind of crazy. We'll do the second one first, okay? The one that makes sense is let's just explore regions of the tree that make sense to explore, right? Parts of the tree that we think are going to improve the decision at the root, those are the ones we're going to spend our time on. Pretty simple idea. It's very similar to heuristic search, right? We're going to spend most of our computational resources on the things we think are promising. So that's not that weird of an idea. The other thing is we're going to do evaluations for a particular state. We're not going to have this evaluation function anymore. Instead, what we're going to do is we're just going to play a bunch of games from that state. This kind of should feel a little weird, right? So we're going to estimate the value of a state by playing a lot of games. If you like playing games, I mean, that could be more fun. But like, why is this going to be good, right? We're no longer like estimating a value by doing a tree search. We're just running a particular policy through this game and seeing what happens. Question? Okay. Yeah, so what does that look like? It means like we're playing Go, right? So we get in this position. We want to know the value of this state, okay? And what we do is we just start playing the game. Maybe we're taking moves randomly. Maybe we have some evaluation policy. The fraction of the wins, having done all of that, we run all these rollouts to the end. The reason they're called rollouts is that they started with this, I think they started with this in backgammon, so they would actually roll the dice. So you have to roll out the whole game. But yeah, so you do all these rollouts and you count the win rate for this position. And higher win rate positions will end up having a higher evaluation. So here's like version 0 of this algorithm. Okay, this one is just going to pick the move that gives the best outcome. Okay, so we're going to run a bunch of rollouts on each node, right? So we're doing our minimax thing, but then when we get to here, we're going to do rollouts. So this is the Monte Carlo tree search part. So we get to the Monte Carlo bit and we say, all right, we'll run our rollouts 100 times from each of these nodes. We get 57 wins, we get 39 wins, we get 65 wins. And now it's time to make a decision for the blue node. Well, let's just go whichever one had 65 wins. That seems like the best one, right? That's version 0 of Monte Carlo tree search. Super easy. Okay, what if this was the result of doing all those rollouts? What if instead we had 57 on the first outcome, we had 100 or 0 out of 100 on the second action, and we had 59 out of 100 on the third action? So this feels a little wasteful in the middle, right? Like, we didn't win at all, and we wasted 100 rollouts on that thing just to know that we were never going to win. Did we really need to do that 100 times to know that? These ones probably looked better a lot quicker than this 100, right? So what if we spent some of that rollout budget on these other ones, right? Can we actually can we allocate the rollouts to the more promising nodes? And that's the sort of second innovation. So now we take 10 rollouts from this center action. We figure out that we still aren't winning at all, and we allocate the remaining 90 rollouts to these other two actions. So now we get 77 out of 140, we get 90 out of 150. I think that one's slightly better, so then we would take that action. So that's version like 0.9. There's a version 1 coming. Does that make sense? Okay, here's the problem with that. So what if the rollouts gave us these values, right? So it's 61 out of 100, 6 out of 10, and 48 out of 100. Let's suppose I had like one more rollout, or maybe I had 10 more rollouts. Where should I allocate my next rollout? What's the best use of my resources here? Well, this one on the right doesn't look that good, so probably don't want to waste it on that. So now I'm just deciding between 61 over 100 and 6 out of 10. Roughly about the same ratio, but this one feels a lot more precise, right? Like, I've spent a lot longer doing rollouts here. I have a lot more confidence in this one because I have a lot more evidence that it's about there. This one seems a little bit more uncertain. I haven't tried it as much. And so version 1.0 says, yeah, when you're uncertain about certain nodes, you're gonna allocate more resources to the uncertain nodes also. So allocate more to the promising nodes, allocate more rollouts to the uncertain nodes. Okay, that's Monte Carlo tree search. We implement that using sort of a heuristic, which basically says how much is it worth to open up this particular state. And that's going to be a function of both the win rate, which is this fraction here. Just the math is a little scary, but we can actually cross out one term right away because it's a log inside of a square root, so it's actually just going to be pretty small. So let's just cross this term out. Don't worry about that. This term here is the win rate. U is the number of wins, the total utility of the rollouts. N is the number of times you tried that node. So this is just your win rate fraction. And then there's a constant times basically the square root of 1 over n. So this says as n gets really, really big, when I've tried a node a lot of times, this is just 0. So the right-hand side cancels out completely, and then we're just left with the win rate. So when all the branches have been tried an equal number of times and that number is really high, then we just care about the win rate. But when n is low, then we're going to get a bonus for the things that we haven't tried yet, and it's going to be proportional to this constant here. OK, so this part is not super important yet. It will come back up when we talk about bandits. Turns out that you can prove that this is a really good heuristic for bandits. But it's not the same problem that we face here. Here we face trees, and bandits are slightly different, which we'll find out later. So we have to modify this slightly. We get something called upper confidence bound applied to trees, which is called UCT. Basically what's going to happen is we're going to go through this tree. Looking at the current state, we're going to expand nodes that seem useful. We're going to expand nodes that seem like we haven't tried them that much. And we're going to do rollouts from those nodes until we run out of time. We're going to update the win counts, and we're going to allow ourselves to continue to do this sort of like trade-off between what have we not seen that much of yet, and what do we think is going to be really good for us. We're just going to choose the action leading to the child with the highest count at the end. So that's MCTS. Here's a quick example before we run out of time. So essentially, we're doing a minimax search, and we're going to need to do rollouts. Let's suppose we expand this node because it hasn't been tried that much. So far, we're 0 for 1 on that node. We have 1 0 times. We've looked at it once. We try this. We're going to do a rollout. Maybe this leads to a win. So we update that particular node. Now it's 1 out of 2 instead of 0 out of 1. We're going to back that up. It's going to go 5 out of 10 to the top node. And we just keep doing that as long as we have time. And you might say, like, well, where's the mins? Where's the maxes? How is this thing going to do anything like optimal behavior? So it's not guaranteed to be optimal unless you run this sort of for an infinite amount of time. But the nice thing is, because you're allocating resources to the things that look good, and you're also allocating resources to the things you haven't tried yet, if you spend an infinite amount of compute, then you're going to try everything because it allocates more resources to the things you still need to try. And by that point, you'll be spending most of your resources on the things that are good. So it'll end up doing the max thing also. So you're allocating more resources towards the good things, and then you're definitely sure that you're going to see everything. So as n goes to infinity, we have this guarantee that it essentially converges to the behavior of max and min, and it selects essentially the minimax move, which is kind of nice. But of course, this is a guarantee for n approaches infinity, so take it with a grain of salt. Still better than nothing. In summary, games are complicated. They require decision-making that can depend on the other adversaries in the game. And so we can handle that with the minimax approach. We can handle that with the Expectimax approach. We can handle that with sort of combinations of the two. It requires computing things efficiently because these search trees get really large. And alpha-beta pruning can help in some cases, minimax especially. Limited depth can help us. Monte Carlo tree search can help us. That's like a very state-of-the-art algorithm, so now you've seen one of those. And it produced a lot of important research, like the checkers work led to self-play in checkers, which led to sort of reinforcement learning. Iterative deepening came out of chess. This meta-reasoning idea, thinking about what the other player's thinking about. And then Monte Carlo tree search is how we solved Go. And different solution methods for things like poker led to how we can solve partial observable games. So that's really good. Video games are a lot harder. We have a ways to go yet. But yeah, that's the lecture on games. Next time we'll talk about logic.